Hi there, this is Professor Shannon Gracey from Maricosta College. Today we'll be going over section 4.1 from the Larson and Edwards Calculus text, and this covers antiderivatives. So we're going to learn about differential equations and how to write the general solution and particular solutions of a differential equation. And we'll learn how to, what the notation is for indefinite integrals and the basic integration rules. So whether you're in my class or you're in someone else's class or just learning all of this good stuff for your own edification, you have to have this stuff totally memorized before you go on to the section where you cover the fundamental theorem of calculus, which is 4.4 in this text, and integration by substitution, which is 4.5 in this text. So are you ready? Let's get warmed up. So here, these are all derivatives. So think about, after you've differentiated something, think about what it would look like. And so think if you can come up with an original function that you had before differentiating. Okay? So pause the movie and warm it on up and we'll see what you got. Okay, let's see how you did. So for this first guy, we have, this derivative is 2 times x. So remember when you use the general power rule, what happened, right? So if you kind of remember d dx of, we'll just say x to the n, what did we get? We got, good, n times x to the n minus 1. So the power decreased by 1. So if we thought of this guy as x to the 1, then the original function would have had to be, good, you would have had to have, so call it capital F of x without the prime, you would have had to have an x squared for sure. Now, you've got that 2 in front there, right? So let's check it out. If you differentiated both sides with respect to x, what would happen? You'd get capital F prime at x is 2x. Now, is that the only answer? No, right? Because you could get capital F at x is equal to, good, x squared plus 1. Or, hey, how about capital F at x is equal to x squared minus 1,000, because when you differentiate a constant, it zeroes out. Good so far? Awesome. So now let's look at some of these other guys. Sorry about the spacing. Not sure quite what happened when it went to print, but here we are. So this guy, the result after differentiating was x cubed. So here we know for sure what? That capital F at x would have had to have, good, an x to the 4th there, right? And notice that there's no constant in front of the differentiated function. So what does that mean? That means when the 4 dropped down, it was divided out. So wouldn't you have to have a 1/4 in front for us to get a derivative of x cubed? Good. Now, is that the only one? No, right? We could have capital F at x is 1/4 x to the 4th minus 12, etc., right? There's many, many options. Now, this guy, do you see, can be written as x to the minus 2. So if something was, decreased and you got by 1 and you got a result of -2, the original function might have been capital F of x is, good, we would have had an x to the minus 1, because when you take away 1 from that, you get -2. Now, what else would we need to have? Because we would have, when you brought that down, you would have had a -1. So good, we would have had a negative. And again, we could have had a capital F at x is equal to negative x to the minus 1 plus 1/5. We could have had a constant that zeroed out. Okay, what about this guy? Great. when you differentiate the tangent function, you get secant squared at that angle. So we could get this guy. We could say, 5 plus tangent at x, right? There's many that we could find. How about getting a result of sine x? Capital F at x. So differentiating which function gets you a sine at x. Good. It could have been cosine at x. But when you differentiate cosine at x, what do you get? You get negative sine at x. So do you see you'd have to have a negative sign there? And then, of course, anything, this could be 25 minus cosine at x would give you the same derivative. And what about this guy? Good. Capital F at x, right, would be, one of them could be 6x to the 1, right, because the derivative of that is just 6. We could have had capital F at x is 6x plus 207. I don't know. I'm just kind of making stuff up here. Any constant. So basically any vertical translation is going to work. So here we go. Definition of an antiderivative. So a function f is considered to be an antiderivative of f on an interval I if capital F prime at x equals f at x for all x and I. So why is f called an antiderivative of f rather than the antiderivative? Good. We noticed that a constant could have zeroed out. So basically, all functions which are vertical translations of each other have the same antiderivative. Okay, so let's check out the next part. The way we represent antiderivatives. So this notation, it's good to know. It can be a little bit confusing, but capital F is an antiderivative of this lower f on an interval I. If that's true, then G, capital G, is an antiderivative of f on the interval I if and only if G is of the form G of x equals f at x plus c for all x and I, where c is a constant. So basically, an antiderivative can be anything that doesn't have this constant of integration added. But a complete antiderivative is when you have the antiderivative plus the constant of integration. So the notation looks like this. So you have something along these lines, the integral of f at x with respect to x, right, equals capital F at x plus c. So this part together, right here, is our g at x because it includes the antiderivative plus the constant. All right, so over here, what we have here is, let's put it in words. This says an antiderivative with respect to x is, right? So if you kind of break these things down, this dx part literally is translated as with respect to x. So if we had dt, it would be good with respect to t, right? And so that's an important one to remember. So now let's just kind of play around with how would that look to us. So suppose that we had something like this, dy dx equals x cubed, right? Well, notice that the dx is not part of the denominator, right? So if we multiplied both sides by dx, then we would end up with this dx dividing out. So we would get dy is equal to x cubed dx. And this is really 1 dy. And just like the derivative is a linear operator, which means you can apply it to both sides of an equation, so is the antiderivative. So you can anti-differentiate each side. So what we have is, good, this one will be y, right, because y is the with respect to variable. And then this guy will be the one like what we'd been working with before. So remember, we got 1/4 x to the 4th. And then what would we add? Good, our constant of integration. So basically, this whole thing right here, this whole thing is this. And this guy over here has this result. And we only need to add the c once, because when you add two constants, you would just get another constant. Okay? All right, so let's check out this next example. This problem is saying, hey, the antiderivative of 8x cubed plus 1 divided by quantity 2 times x cubed with respect to x is equal to this step on the right side. And so if we verify this, we can differentiate the right side, and it should equal the integrand of the left side. So basically what's inside the integral. So let's check it out. 2x to the 4th minus, how else could we write that? 1/2 times x to the negative 1 plus c, and we need to differentiate this, and we want to know, hey, is this equal to 8x cubed plus 1/2 x to the negative 2, all right? So differentiating the left side, what happens? Good, we'll get 8x minus 1/2 times negative 1x to the negative 2. And then what's the derivative of a constant? Good, it's 0. We want to know, is this equal to 8x cubed plus 1/2 x to the negative 2? Well, we will get 8x plus 1/2 x to the negative 2 equals 8x, oh, sorry, this is cubed, 8x cubed plus 1/2 x to the negative 2. So that checks out, so we have verified the statement. Good so far? So basically, what does that mean? You can always check your work. You can check that you got the correct antiderivative by differentiating your result and seeing if you get what's inside the antiderivative. or the integral. All right, so this next example wants us to find the general solution of the differential equation. So just like we did before, we want to multiply both sides by dx to get it in the right spot. So notice it'll divide out on the left side and we'll get dy, which remember was just 1 dy. And then that'll be equal to 2 times x to the negative 3 dx. Integrating both sides, we'll be integrating with respect to what variable on the left? Beautiful, y. And we'll be integrating with respect to what variable on the right? Awesome, x. So what will we get? Great, y, because the derivative with respect to y of y would just be 1, actually, is equal to, so what would we have started there? We would have had to have x to the minus 2, right? The constant goes along for the ride, and we would have had to divide out what? So we have our 2x to the negative 2, but remember, we would have been multiplying by negative 2, so we need to divide to adapt, and then plus our constant of integration. So at the end of the day, we would get, good, y is equal to negative x to the negative 2 plus our constant of integration. All right, so let's take a look at this other one. What do you think we should do first? Beautiful. Multiply both sides by d theta. And then the d theta will divide out over here. And what are we going to have? We're just going to have 1 times dr is equal to pi, which is a constant, times d theta. So evaluating the integral of both sides, what do we get? Awesome. We'll get r is equal to pi times theta. Good so far? Great. What did I miss there? Plus c, plus our constant of integration. Awesome. Okay, so let's just go through. You need to know all these formulas. So the derivative with respect to x of a constant is 0. So therefore, if you're integrating 0, okay, so you won't ever see this normally, but when we have the antiderivative of 0 with respect to x, normally you're just going to see a 0 there, or you won't see anything at all. So this basically equals our constant of integration. Okay, so far? All right, so when you're differentiating a constant times x with respect to x, you just get that constant, remember? And so therefore, when you're finding the antiderivative, you'll get, good, the constant times x plus our constant of integration. And the derivative of a constant times a function is the constant times the derivative of the function. So when you are anti-differentiating a constant times a function, you'll get your constant times the antiderivative of that function with respect to x, and that's going to equal to the constant times that capital F of x plus c. All right? Okay, so when you have the derivative of a sum or difference of functions, you get the sum or difference of the derivative. And over here, when you evaluate the antiderivative of a sum or difference of functions, you will end up getting the sum or difference of those antiderivatives if you wish to break it up. So the dx goes into both of them, like it just distributes in there, and you'll get this result. Good so far? Great. Okay, so when you're using the power rule with derivatives for x to the n, remember that you get n times x to the n minus 1. So here, what's going to happen is you're going to get x to the n plus 1 divided by n plus 1. So you're going to divide you're going to raise the power by 1 and then divide by that result, okay? And what else will I have to do? My constant of integration, and then what? What do we have to exclude for n? Good, n cannot equal to -1. We'll learn about that more in chapter 5, what we get. Okay, so derivative with respect to x of the sine function gives us the cosine function at x. And when we're anti-differentiating our cosine function, you got to be careful because we'll just get sine at x, so you have to test it. If you differentiate sine at x plus c, make sure your sine's right, and it is. You'd get cosine at x, and that's what's in the integrand. Okay, so the derivative with respect to x of cosine at x is negative sine at x. So when you're anti-differentiating sine at x with respect to x, you know you'll get a cosine at x plus c, but is that cosine at x going to be positive or negative? Good, negative, because when you differentiate negative cosine at x plus c, you would get negative sine at x plus 0, which is sine at x. All right, so continuing, remember that you get secant squared at x when differentiating tangent at x. So here we'll get beautiful tangent at x plus c. Continuing, derivative with respect to x of tangent at x is secant at x times tangent at x. And anti-differentiating, we'll just get secant at x plus our constant of integration. This guy will give us negative cosecant squared at x. So here, what do you think? We know we'll get cotangent at x. We got to make sure our sign's okay. Good, we're going to need a negative, aren't we? Negative cotangent at x. So when you differentiate cotangent at x, you get negative cosecant squared at x. Okay, so continuing along, we get negative cosecant at x, cotangent at x, and then we'll have, good, negative cosecant at x plus c as our antiderivative. Good so far? Great. Okay, so let's go ahead and apply all this lovely stuff. So we're going to find the indefinite integral, and we're going to check our result by differentiation. So here, basically, if we use the rule that the integral of a difference is the difference of the integrals, we would have the antiderivative of 16 with respect to x minus the antiderivative of x with respect to x. Remember, this is like your x to the 1. So this one, a constant, the antiderivative of a constant is just going to be the constant times whatever variable you're differentiating with respect to. Now over here, minus, so we're going to do x to the 1 plus 1 over 1 plus 1. And then don't forget plus our constant of integration. So this will give us a result of 16x minus x squared over 2 plus our constant of integration, and we're all set. So the nice thing here, if you're in my class, is that we don't need to write antiderivatives as one happy rational expression. We can just keep it like this. Okay, so one of our strongest tools that people forget about is algebra. So here, notice that there was no rule for the quotient of two functions. So what that means is we have to turn this into a difference of two functions. So how do we do that? Good, we rewrite it. So this is the integral of, remember it goes power over root. So we have x to the 3/5 minus 2x to the 1, and that's being divided by x to the 1/2, and this is with respect to x. So if we go ahead and divide each of those terms, we'll have the integral of x to the 3/5 minus a half, because when you're dividing, let me do an extra step. We'll have x to the 3/5 divided by x to the 1/2 minus 2x to the 1 divided by x to the 1/2 with respect to x. So now when you divide same bases, what do you do with the exponents? Good, you subtract them. So x to the 3/5 minus 1/2, and then minus 2x to the 1 minus 1/2 with respect to x. So this will give us the antiderivative of x to the, what? 6/10, right? Minus 5/10. So I think that's 1/10. And then minus 2x to the positive 1/2 with respect to x. So now if you want to split them, you can. So you'd have your x to the 1/10 dx. You don't have to split them if you don't want to. And then remember that we can factor out that 2, bring the 2 out of the antiderivative. And we'd have our x to the 1/2 dx. So then what would happen? We'd use our general power rule. So we're going to do x to the 1/10 plus 1 divided by 1/10 plus 1 minus 2, the 2's going along for the ride, times x to the 1/2 plus 1 divided by 1/2 plus 1 plus our constant of integration. So then x to the 1/10 plus 1 is going to be what? Good, x to the 11/10. So we'll get 1/11 times x to the 11/10. Whoops, no we won't. I'm making up my own math here. Let's see. We'll have, I'll just work it out longer. So we have x to the 11/10 divided by 11/10 minus 2 times x to the 3/2 divided by 3/2 plus c. So this is going to give us what? 10/11, because you'll invert and multiply, x to the 11/10 minus, great, 4/3 x to the 3/2 plus our constant of integration, and we're all set. How's it going so far? All right. So now we will be learning a rule about differentiating composite functions, but right now we don't have that tool. So what can we do? I mean, we have to turn this into a sum or difference of functions. Do you see that? To be able to complete this problem. So I don't know if I showed you Pascal's triangle before, but basically with Pascal's triangle, the idea is, however you want to expand this out, you'd need to expand it out. So with Pascal's triangle, if you've got, a plus b to the 0 power, you get 1. So that's like the top of the triangle. A plus b to the 1 power ends up being 1a plus 1b. So you end up getting, in your triangle, you end up getting like 1, 1, 1. And then a plus b squared is 1a plus 2ab plus 1b, and these are squared on the end. And so notice that every term has a degree of the power you're raising that binomial sum to. So this was 1, 2, 1. So it turns out, as you go on, so a plus b cubed will give us 1a cubed plus 3a squared b to the 1 plus 3ab squared plus 1b cubed. So that gives us 1, 3, 3, 1. So what would the next one be? Do you see how you're adding to get the middle? Good. The next one, a plus b, that quantity to the fourth, would be 1, 4, 6, 4, 1. So this is just a quick way to get your coefficients. So with that in mind, this is going to be equal to the integral of one. You know what? I'm going to do this below here. So what was it? 3x minus 4 cubed. So therefore, 3x minus 4 cubed could be written as 3x plus negative 4, the quantity cubed. So your a would be 3x and your b would be negative 4. So expanding, what would happen? You would have 3x plus negative 4, the quantity cubed, will be 1 times 3x cubed plus 3 times 3x squared times negative 4 to the 1 plus 3 times 3x to the 1 times negative 4 squared plus 1 times negative 4 cubed. So that's going to give us 27x cubed. And then we'd have what? 9 times negative 4 is negative 36. And negative 36 times 3, I think, is minus 108. And then x squared. Let's do that, 36. Yep, 108. And then we'll have, let's see, 16 times 9, I think, is 144 times x to the 1. And then minus 64. So bringing that guy in to our integral, we can say this is equivalent to antiderivative of 27x cubed minus 108x squared. What's the next one? Plus 144x. And then minus 64 with respect to x. So now this is just ends up being a sum or difference of functions. So this is going to give us, I'm going to do it all as one big happy deal. So 27 times x to the 4 plus 1 over 4 plus 1. And then minus 108 times x to the 2 plus 1 over 2 plus 1 plus 144 times x to the 1 plus 1 over 1 plus 1. And then lastly, minus 64 x's plus our constant of integration. So now what's going to happen? We'll get 27 fifths x to the 5th. And then what? I think we can divide 108 by 3, right? So that would be 36 minus 36 x cubed and then what? Good, we'll have plus 170, or no, plus 72 x squared minus 64 x's plus our constant of integration, and we're all done. How you doing? Okay. So now, again, starts with an A, not a bad word. Algebra. So this guy, there's no rule for the integral of a product of two functions. So we can write this as the integral of, first of all, I would recommend writing everything with rational exponents and then distributing this guy through. We'll have the integral of u to the 1/2 minus u to the 3/2 with respect to u. And now we're ready to integrate. So what's going to happen? We'll get u to the 1/2 plus 1 over 1/2 plus 1 minus u to the 3/2 plus 1 over 3/2 plus 1 plus our constant of integration. So that'll give us u to the 3/2 over 3/2 minus u to the 5/2 over 5/2 plus c, which will give us a result of, good, 2/3 u to the 3/2 minus 2/5 u to the 5/2 plus our constant of integration. All right. So next up, we now have this integral here. So again, we're going to have to multiply, right? Because we have no rule for the integral of the product of two functions. So this will be equivalent to the integral of secant at t times tangent at t minus secant squared at t with respect to t. Now, let's go ahead and split the integral. So this would be secant at t times tangent at t with respect to t minus the integral of secant squared at t with respect to t. So what is the antiderivative of secant at t times tangent at t? Beautiful. Secant at t, and then over here, minus tangent at t plus c. So just in case you're having trouble matching up, this whole thing has an output of secant at t, and this whole thing here has an output of tangent at t. And we're done. All right, so next up we have 4 theta minus the antiderivative of 4 theta minus cosecant squared at theta d theta. So here again, I don't know if you want to split the integral. You don't have to, but using our properties, this would end up being 4 times the integral of theta d theta minus the integral of cosecant squared at theta d theta. So we would get for the first one 4 times, this is theta to the 1, right? So it'd be theta to the 1 plus 1 over 1 plus 1 minus, what is the antiderivative of cosecant at theta, the quantity squared? Good, it's negative cotangent at theta plus c. So here, again, this antiderivative is represented here, and this antiderivative is represented here. And so we would get 4 over 2 is 2, so 2 theta squared plus cotangent at theta plus c. And we're all done. Okay, so next up, this one takes a particular trick, all right? Please remember that if you have, 2 terms in the denominator, you can't split that denominator ever. So what we want to do is yield a difference of squares situation so we can use trig identities. So this is called using Pythagorean conjugates to change this integrand around. So basically what we're doing here, what would I multiply 1 minus sine of x to get a difference of squares? Good, it'd be 1 plus sine of x. And you've got to balance it out by doing that in the numerator and the denominator. And then we still have this with respect to x going on. So then we'll have the integral of 1 plus sine of x times 1 is 1 plus sine of x over 1 squared, which is 1, minus sine squared at x with respect to x. But isn't that an identity? Good. We'll have 1 plus sine of x going in the numerator, but in the denominator, isn't that cosine squared of x using the Pythagorean identity? So here, this expression, and I haven't integrated anything yet, that expression is equivalent to cosine squared of x. So continuing, we will have this is equal to, if I divide each term in the numerator by cosine squared at x, I'm trying to make this look like one of our basic rules, right, for integration. So this guy, do you see, is secant squared at x, right, with respect to x. I'm going to split that integral. And then this one, do you see, is what? The integral of sine at x over cosine at x times 1 over cosine at x dx. With me so far? Awesome. So now this one will be, I'll just keep it going, secant squared at x dx plus the integral of tangent at x times secant at x dx. So what will these be? Beautiful. Tangent at x for that first one. Tangent at x times secant at x is the same as secant at x times tangent at x. So that'll have a result of secant at x plus our constant of integration. So this guy here had this result, and this guy here had this result. All right? Doing okay so far? All right. So now let's talk about initial conditions and particular solutions. So you've already seen that the equation y equals the antiderivative of f at x dx has infinitely many solutions. Each differing from each other by a constant. So as we spoke of earlier, this means that the graphs of any two antiderivatives of f are vertical translations of each other. So here, basically, if you have, something like from the warm-up, we had 2x, the integral of 2x with respect to x, and that was equal to x squared plus c, right? So if we're thinking of, what that graph would look like, we would have, we would have these infinitely many parabolas. So we'd have so let's do I don't know, we could have the first c just be 0, right? And then this next one, we could have be x squared minus 5. We could have this one be x squared plus 7. And we'll do one more. Have this guy be x squared minus 2. So let's graph these guys and check it out. Right, so basically, you know, if you said, oh, okay, you know, C1 is 0, what else did we say? C2 was going to be negative 7. C3 was, or was it negative 5, right? Negative 5. C3 was positive 7, right? And then C4, I think we said, was negative 2. Right? And so, you know, this this one is the black, is the first one is the blue graph, right? Right here, when C1 is 0. And then we've got the green graph was that guy. The black graph was this one, and then the pink graph was that guy. So anyway, you've got these family of antiderivatives. So in many applications of integration, you're given enough information to determine a particular solution. To do this, you need only know the value of y equal capital F of x for one value of x. So this information is called an initial condition. So let's think about this. How do the following statements differ? If you have x squared versus y equals x squared, the first one is good, an algebraic expression. And the second one is an equation. Now, what about over here? How about y equals x squared versus dy dx is x squared? So this is a regular equation or function. And this here, this guy is the derivative, so it's differentiable, so it's a differential equation. Okay? All right, so let's check these out. Let's solve the differential equation. So we've been given that g prime at x is 6x squared and g at 0 is negative 1. So let's write g prime at x as dy dx equals 6x squared. And then what was the trick? Beautiful. Multiply both sides by the dx, and then we'll get dy is equal to 6x squared times dx. And then what should we do? Awesome. Integrate both sides. The integral of 1 dy is good, y. And this guy is going to be 6x to the 2 plus 1 over 2 plus 1 plus our constant of integration. So we'll end up with y equals, what, 2x cubed plus c. So now let's rename it g of x is 2x cubed plus c. So g at 0 is -1. So that means that when the function takes on a value of -1, the input has to be 0. So -1 is your c. So now writing our function, we're going to have what? G of x is equal to 2x cubed minus 1. All right? Groovy. All right, so now what do we have? We've got a second derivative at x is sine at x. F prime at 0 is 1, and f at 0 is 6. So here we go. Let's take a look at this as this ends up being d squared y over dx squared is sine at x. So if you multiply both sides by dx, what will happen is one factor will divide out, right? And what we'll have is what? We'll have d dx of dy is equal to sine at x dx times dx, right? And so now, integrating, what we'll have here is this part will just take on y. So we'll end up with dy dx is equal to, good, negative cosine at x plus c. And then, now again, that gave us what f prime is, right? So here, f prime at x is equal to negative cosine at x plus c. We've been given that f prime at 0 is 1. So 1 is equal to -1 plus c. So our c, we'll call this c1. So our c1 is 2. And so that means that we'll have f prime at x is negative cosine at x plus 2. So that's the first one. That's like our first part of the problem, right? So now, switching this back into Leibniz notation, we'll have dy dx is negative cosine at x plus 2. Multiplying both sides by dx, we will have dy is equal to negative cosine at x plus 2 with respect, or dx. And then integrating both sides, we'll have, perfect, y is equal to negative sine at x plus 2x's plus c. So then, that tells us that f at x is negative sine at x plus 2x plus c, call that c2. So now we were given another initial condition that f at 0 is 6. So we have 6 equals negative sine at 0 plus 2 times 0 plus c2. So 6 is equal to C2. And our final solution. So our solution at the end of the day will be f at x is equal to negative sine at x plus 2x plus 6. And we're all done. All right, so the next couple sections kind of depart from this. So you got to make sure that you really learn these well and remember all the formulas so that when we get to 4.4 and 4.5, things go much easier for you. All right, so have a fabulous day. Bye.